All right, so question number 15, we have an amusement park with a ride that has a mass of 300 kilograms, 4 passengers, 60 kilograms each, and we're dropped from a height of 120 meters. Frictionless path, loop-the-loop, 30-meter radius, and then we enter a stretch from A to C where friction brings it to rest after 40 meters. And of course, someone wrote in our textbook, so everything is nicely highlighted for us. So A, find the velocity of cart at A. B, find the reaction force from the seat of the cart onto the passenger at B. And then C, what is the acceleration experience by the cart from A to C, assumed that is constant. So let's tackle these in order. So A, find velocity at A. And so I'm going to use the concepts of energy to do that. We know at the very top, right? So we're just, let's make that a little bit prettier. So we're just have this path here, right? So we know at the beginning, we just have gravitational energy. It doesn't say anything else about it moving right there. And then at A right here, we're gonna have simply kinetic energy because our zero height is just gonna be here, right? So height equals 0. So all of our gravitational energy is going to be converted into kinetic energy as long as there is no friction. And so mgh equals 1/2 mv squared. It doesn't matter if there's riders or not because my masses are going to cancel out. And so we're left with that the velocity is going to equal 2gh square root. So plugging that in, that's going to be 2 times 10 for gravity times 120. Square root, and the velocity at A is going to equal pretty much 49 meters per second. Okay. Second part, find the reaction force from the seat to the cart onto a passenger at B. Well, as we continue along our path, right, we need to know that when we're at B. So let's draw the scenario, right? So here we are. So here's A, right? And then B is obviously right here. So we have the force of gravity acting down. We also are going to have a normal force acting down as well because it's on the underside of this loop. So that normal force is going to be pushing it downwards. So if we're just talking about a single passenger, right? Find the reaction force C onto a passenger, right? So our mass is going to be 60 kilograms. And our equation, the sum of the forces in the y direction is, let's make it easy. Let's make the positive direction down. So that's going to be the force of gravity plus my normal force equals mass times acceleration centripetal. And so the force of gravity plus the normal force equals my mass times v squared over r. Now, we got to be careful when we jump into this because while the velocity was 49 meters per second here, as it goes back up, we are going to be losing velocity because that velocity is going to be turning back into potential energy. So we're losing kinetic, turning into potential. So if we look at the original problem, right, this is where we're at here. And so let's just say that this has a height of 0 there. And so for our situation at B, we can say this is the gravitational potential energy, and this is our kinetic. If we do that, then the height that it traveled, right, is simply 60 because we have 30 here plus another 30 is 60, and the total height is 120. So we can just say that we had a change in potential energy due to a height of 60 meters instead of 120. It really doesn't matter which way you do it, and I'll show us that either way actually works. So let's first find velocity at B using energy. Okay, and so if we said, like I had just shown, that EG equals kinetic energy, we're going to have mgh equals 1/2 mv squared. And just like we just saw, we saw v equals 2gh radical. 2 times 10 times 60 square root. And that's going to give me a velocity of about, I believe it's 34.6 meters per second. Now, if you had chosen to have, if we draw this, if we draw this here, and you had chosen to draw this, and you said this was my height equals 0 there, you'd have gravitational, plus kinetic, and you'd have EG equals EG plus kinetic, mg 120 equals mg 60 plus 1/2 mv squared. We still get all of our m's to go away. And we would simply have, 120 g equals 60 g plus 1/2 v squared. We would need to get this to the other side, and so we'd subtract 60g, and so that'd be 60g equals 1/2 v squared. So we would still get 2 times g times 60 square root equals my velocity. So either way, we're going to have the same thing, okay? This and this are the same result. So what we need to do, though, was first just find our velocity at B. Now we have our velocity at B. We know the radius. We know our mass. And so we can now solve for the normal force, which is the reaction force of the seat pushing down. Okay? So to do that, we'll say, let's go back to purple. We'll say force of gravity is mg plus Fn equals m v squared over r. And I'm just going to solve for Fn first. So I'm going to subtract mg from both sides. So I get Fn equals m v squared over r minus mg. M v squared over r minus g. 60, 34.6, 30, 10. That's going to give me 1,800 newtons. So that's how big the chair is pushing back down on the passenger. All right, and then the last part says, what is the acceleration experienced by the cart from A to C, assumed constant? So again, here's our picture. Boom. So from A to C, again, our velocity at A is going to be back to 49 meters per second. And so let's say this, that's our initial velocity at A. Our final velocity at C is going to be 0. We also know that the distance it covers is 40 meters, okay? So I'm just going to use my kinematic equations because we're simply trying to solve for A. And so with that, I can say initial velocity, final velocity squared equals initial velocity squared plus 2 times my acceleration times my displacement. So again, we're just trying to solve for acceleration. We know that my final velocity is 0. And so this becomes negative u squared equals 2as. So we're going to divide each side by 2s. So acceleration equals negative my initial velocity squared times 2 times my displacement. So negative 49 squared divided by 2 times 40. And I would get an acceleration of negative 30 meters per second squared. And that negative should make sense, right? If this is the positive direction by indicating that we had a positive 49 here, so that's obviously the positive direction. My acceleration then should be facing in the opposite direction, because we're causing it to slow down.